I think that we can pass to the second speaker, Vittoria Sposini. Okay, I'm going to present Vittoria. If you want, Vittoria, you can start sharing your screen.
I think we are still seeing Brandon's screen.
Okay,
okay, perfect. Yeah, thanks.
Okay, so Vittoria got a Master of Science in 2016 at the University of Bologna with Castellani and Pagnini, and the title of the thesis was a numerical study of fractional diffusion through a Langevin approach in random media. And in 2020, she got a PhD in mathematics and statistics at the University of Potsdam under the supervision of Ralph Messler, and the title was The Random Diffusivity Approach for Diffusion in Heterogeneous Systems. And since a couple of years, she's in Vienna, at the University of Vienna, and she's a postdoctoral fellow, and she's working on Glassy phases of the Gaussian Core Model, and this is the title of her talk today. Thank you, Vittoria. You can start.
Thank you. Can you see my screen?
Yes, we can see it.
Perfect. Thanks a lot for the introduction. So as said, I will mostly talk about the last work I've been carrying out with my basically my supervisor here in Vienna, Christos, and another collaborator, Manuel Camargo. And the talk will focus on these glassy phases of Gaussian Core Model. Just to give you an outline of the talk, I will spend mostly like the first, let's say, half of the talk to give a general introduction, spanning through, like, in general, what I mean by slow dynamics of glass formers, introducing post-colloid suspensions, and the actual model that I will describe. And then I will give you an overview, very brief overview of what's the state of the art on the glassy dynamics of the model that I investigate. After that, I will scroll through the methods, meaning that I will discuss the simulation details, as the work that we've done is mostly a computational work. And then I will just present results which are based essentially on characterizing what is the flow dynamics of the Gaussian Core Model in low and intermediate density regime. And finally, I will move to conclusions and outlook. So jumping into the introduction, what I would like to start with is to give you an idea of what, or let's say, like, what I mean by slow dynamics of canonical glass formers. But first of all, by canonical glass formers, I mean all those systems, let's say, that we know that are able to actually create a glass and have been studied over the years to sort of understand what is the typical dynamics of glassy systems. And all these models are usually based on the interparticle potentials, which are short range and strongly repulsive. For instance, we can think of the hard sphere systems like Lennard-Jones potential, WCA potential, and so on. And all these canonical glass formers have in common that basically the repulsion is what dominates the physics of the system. This means that the thermodynamic and the dynamical properties are mostly emerging to the strong repulsion that we have in the system. This means that actually qualitatively all these systems behave similarly. This is why here I can just present you some results on the Lennard-Jones systems, but you can keep in mind that all these other canonical glass formers actually are behaving very much similarly to what I will present you here. For instance, there are a lot of work focusing on these canonical glass formers and their flow dynamics. And here I took, for instance, this paper just to show you the main properties that I'm interested in. And as you can see, basically, we have this system of Lennard-Jones particles. And this is a binary mixture, it's the standard Cobb-Anderson system. And what you see is that when you start decreasing the temperature of the system, you will see that at the level of the mean square displacement, the system will start to develop this plateau. And this is exactly what I mean by slowing down. This means that basically it sort of stops for a moment and then eventually it manages to relax. And this is what happens when you go and basically decrease the temperature and go from orange to blue, let's say. You really see this emergence of the plateau. And if you look at the displacement distribution, what you will see is that instead of having a standard Gaussian displacement distribution as you will have in a fluid system, you start to develop these sort of non-Gaussian tails, which are usually exponential tails, as you can see over here. And the main idea behind this tail is let's say, is explained by the fact that you have some sort of dynamical heterogeneity in the system. And if we look at a single particle trajectory, usually you would observe something like this. I took this for one paper of mine, and you can see that this is the displacement of one trajectory, let's say the blue one, which is identified here in blue. And what you will see is that the trajectory will mostly just oscillate around some cage which is created by the neighbor, so it will just oscillate around, and then eventually it will manage to escape and hop to the next cage and so on. So in a way, if you look at the system, you will have a sort of difference between mobile particles which are jumping around and immobile particles which are just vibrating within the cage. So this means that actually this Glassy dynamics can be very nicely explained by the concept of hops between cage. You have some sort of cage created by the neighbors, and then you just have some hops between cage. So my main claim today actually is going to be that if we look at the Gaussian core model that I will introduce in a moment, this idea of concept of slow dynamics based on the cage mechanism has to be revised, especially at high densities. This is going to be my main claim. So keep in mind this caging mechanism because it will come back later on. But let me now introduce the Gaussian core model. And in order to do that, I'd like to first start in general with soft colloid suspensions and what I mean by that. So soft colloids are, let's say that a lot of systems can be identified as soft colloids. You can think of polymer chains, stars, and rings. And the main features that they have is that they have a very high degree of flexibility and deformability. This is why they are called soft. And in general, if you analyze their suspensions, you will see that they have a very rich thermodynamics and also dynamics. And in particular, very similar to all the canonical glass formers that I just talked about, which mostly come from hard colloids. In the supercooled regime, also the soft colloids will start basically exhibiting this very long equilibration time. So the relaxation time actually will get slower and slower, and you will have some sort of heterogeneous dynamics. Interestingly enough, at very high concentration, which is actually the point at which the softness becomes very relevant, where you're just basically putting a lot of particles together, you're increasing the temperature, the density and the concentration. This means that basically the softness of the particles becomes very relevant. You have very interesting regimes that you wouldn't observe otherwise in hard systems. And from a theoretical point of view, basically the interaction that you have in this system is just a pair potential which does not diverge at full overlap. So if we have a potential which is V of R, and R is the distance between two particles, you would expect that actually for a soft system, R equals 0, it doesn't diverge. So this means that the particles can effectively overlap. They are fully penetrable. Of course, this is not sort of a molecular potential. It's just an effective potential that you can think of. In general, the Gaussian core model represents like a main, let's say, one of the main model in this soft potentials, and in particular, it was introduced in the 70s by Stillinger, and basically it's just a model in which you have an interparticle potential which is Gaussian shaped, so which means that you will have a energy scale which is epsilon, and you have sigma which is your length scale, and the potential looks like a Gaussian. So, and this is very interesting because it has been shown, for instance, that if you have two polymer chains like the light gray and the dark gray here, you can see that if you calculate what is the effective potential of the center of between the center of mass of the two chains, you will see that actually it behaves like a Gaussian. So it's sort of an effective potential that really describes some sort of real system. And the main feature is that it's a purely repulsive potential, so there is no attraction, it's just repulsive. And it's different from other sort of potential like the Lennard-Jones that, for instance, is as well purely repulsive, but it has in our case we have softness in there. And on top of that, it's also long range because you have Gaussian tails, so it's not cut at a specific distance, but it actually has this Gaussian tail. This means that actually we have a combination of softness and long tails that will give rise to very interesting dynamics, especially at high density. So what we know so far on the Glassy dynamic of the Gaussian Core Model, to do that, let me start from the phase diagram. So we have here the density of the system and the temperature. The main property of this Gaussian Core Model is that you have this re-entrance phase. This means that, for instance, if we fix a temperature of the system, which is somewhere over here, the system here will be fluid. Then you increase the density, it will actually become a crystal, it will freeze. But then if you keep increasing the density, after a while, it will remelt into a fluid state. This is due to the softness, and we will see that this is also very relevant for the Glassy dynamics. And what is known is that from theoretical studies, we know that at very low densities, the system behaves more or less like an hard sphere system. So what we would expect is that also if we look at the Glassy dynamics, we expect a standard canonical, let's say, glass form at low density. Instead, if we go to high density, what has been shown already by some simulation, molecular dynamic simulation study, is that first of all, the system vitrifies. It means that actually it's not easy to observe this BCC crystal, but actually the system would rather slow down and become a glass. And you don't need to introduce any polydispersity. Even the one component Gaussian Core Model will just vitrify very nicely. And the whole dynamics is much more rich than a standard low density glass. And this is what we are going to go into the details. The main research question that I have at this moment is that how does the transition from the low density hard sphere glass to the high density glass, in which we have a very different dynamics, how does this look? And can we characterize it? And in order to do that, what we do is that we will focus on this regime over here, which is basically the low intermediate regime, because at high density, actually the Glassy dynamics has already been quantified, as I explained before. So we focus on this intermediate regime. And what we want to do is that this is just a zoom in. The black line is, again, this freezing line that we have over here. In order to approach the Glassy regime, what we need to do is that we need to go down in temperature and avoid the crystallization. And we want to approach the glass line, which is deep into temperature down here. This blue and red line comes from different theories that you can find in these papers if you want, but I'm not going into the details of how we obtain the glass line. It's just to give you an idea that basically what we need to do from our studies, that we need to overcome the crystallization line and go down into temperature, basically deep temperature. Well, in order to do that, basically it's gonna be a bit tricky because it's not simple from a computational point of view to go that deep into the class, because it's very easy to go out of equilibrium and then we cannot really characterize the systems that easily. So what we're going to do now is that actually we will go at a bit higher temperature, so in a supercooled regime, as I showed you before also for the canonical glass formers, and we are going to identify some iso diffusivity points, basically different points in the density at which the system will display the same diffusivity, the same diffusion coefficient. And what we do is that basically we are going to characterize the system dynamics by means of standard quantities, and also we will characterize a single particle dynamics and see whether we see any difference between the low density and the intermediate densities, and eventually the large density. Because the idea is that if there are two different glasses, then even the supercooled regime should show some sort of difference. So in order to do that, what we do is that we are going to use molecular dynamic simulations. And I'm using LAMPS, and I run molecular dynamic simulation in the MBT ensemble. Okay, these are just, we have basically a box with periodic boundary condition. We have around 4,000 particles. We set the temperature and density in a way which are adjusted to our units of the potential. And of course, numerically, we also need to introduce a cutoff, but it's done in a way that we know that the Gaussian, basically the tails of the Gaussian are still relevant for the system. The main point, as I told you, is basically we need to avoid crystallization. To do that, usually people introduce polydispersity in the system. So the way is that basically you need to sort of introduce some frustration in the system such that the system cannot crystallize and it remains a bit fluid. Actually, polydispersity doesn't work that well for this system. So what we do is that we introduce bulk spinning. This means that if you have your box and a lot of particles in the box, which would be the blue particles, what we do is that we select more or less 10% of them, which are the yellow one, and we just freeze them. So those particles are just gonna be there. They are completely frozen and they are not gonna move. And they are just there to create some sort of frustration in the system such that the nucleation cannot happen and the system doesn't crystallize. And it has been shown that this sort of pinning works to approach the Glassy. So how do we prepare the system? We just first equilibrate the pin matrix, which is, as I said, around 10% of the particles at the desired temperature. And then we insert all the other particles, the blue one, and then we just let the system equilibrate for a long time. And after the system is equilibrated from there on, we basically simulate our system and focus only on the mobile particles. Of course, in order to be sure that the realization of the pin matrix that we have selected is not affecting the dynamics, what we do is that we actually run 5 or 10 independent pin matrix, and we average over this, such that basically we remove the effect of the realization of the pin matrix. What we start from is, for instance, we start from just the standard quantities as the mean square displacement, as I showed you before. You will see that the color coding is gonna be always the same. So yellow is a lower density. When we go to red and purple, is usually higher density. So we go from 0.1 to density 1. And as I told you before, we want to focus on basically the point in the phase diagram in which we have isodiffusive lines. And this is, you can nicely see the fact that actually eventually all the curves are overlapping when they approach the diffusive state. This means that basically the diffusion constant is the same. But what you see over here is that basically the slowing down, which is the emergence of this plateau, is actually pretty different from the different density. What I'm putting in the insert is just this gamma, which is basically the logarithm derivative of the mean square displacement, to highlight the fact that the mean square displacement goes from a ballistic, then it has this very sort of deep subdiffusive or also almost plateau state, and then it eventually all of them converge to a nicely diffusive state. So the system is still relaxing. This is just a super cool state. It's not a glass state. So what we can do, other standard quantities are, for instance, we can look at the structure factor of the system, which is in a way the Fourier transform of the radial distribution. And we see that if we basically rescale all of them over the position of the first peak, we see that they mostly actually overlap. So the structure of the system doesn't need to be that different. That doesn't seem to depend that much on the density. And on the side, we also calculate the intermediate scattering function, which is basically just an indication of the relaxation of your system. And here you see once again that basically there is some difference in the way in which the system relaxes to equilibrium. So when it goes to 0, it means that the system has relaxed. And there are sort of different slowing down that the system has at different densities. And then another standard quantity is, for instance, to calculate the non-Gaussian parameter, because as I told you before, usually in this flow dynamics, we always have the emergence of some exponential tail in the displacement distribution, so some non-Gaussianity. Then what people do is that usually they calculate this non-Gaussian parameter, which is basically sort of a ratio between the fourth and second moment, and it's normalized in a way that when it goes to 0, it's the quantity you would have for a Gaussian. So the fact that it starts from 0, because it just starts from Gaussian fluctuations, that you see that there is this emergence of some non-Gaussianity. But very interesting, the non-Gaussianity is much more present in low density system. When you go to pretty high density, actually the non-Gaussianity is much less relevant, which is also what we knew already from the state of the art. So the idea for us would be to understand what happens actually in this system. Why is this non-Gaussianity disappearing, and how are the particles moving around? But before going into that, actually an indication of this can already be seen at the level of the particle displacement distribution. So here it's plotted in a funny way because we are actually plotting it and taking the logarithm of the displacement. And this is done because I want to emphasize actually some short displacement that I will show later on. So what we do is that we fix the time. This is 10 to the power 3 is basically at the time at which the plateau is almost finishing and the system is about to relax. And there you see that everything is still more or less, let's say, unimodal. This is what we care. Then what happens is that when we increase the time, when we calculate the particle displacement distribution at larger times, what you see is that there is a sort of bimodality which is appearing. And this is representing of the hopping. So this means that basically the particles are mostly fluctuating around the cage and then they hop. So there is basically this second peak that emerges is representative of the first sort of neighboring, that they're jumping over the first available cage. But what is interesting is that this bimodality, as you can see, appears for the low density very much. For the intermediate density also is there, but for the very high density is not there at all. And if we increase even more time, once again, for the purple one, which is the very high density, you don't see any bimodality. So this means that actually what we observe from this plot over here is that hopping at high density is highly suppressed. But we knew that hopping is basically the main feature of the slow dynamics of glass formers. So this is an indication of the fact that the dynamical regime at intermediate and high densities is much different. And basically, to do that, we can just go and look at the single particle trajectories. How do they look like? So here on the left, you have, for instance, something like a realization in 3D. But if we look at the models, the displacement, this is one trajectory at different density. You see that actually the trajectories look pretty different. So at lower density, you have this nice intermittent dynamics, as I told you before, that we saw for the standard canonical glass formats. But then the more we go high in density, the more the dynamics seem actually pretty continuous and homogeneous. So this sort of intermittency is disappearing. And basically, I wanted to come up with some method which allows us to actually classify the transition.
Vittoria, you have 5 minutes.
Thank you. Yes. Which allows us to classify this transition. And what we do is that we just use this local convex hull method, which has been introduced recently to exactly do this job, basically to classify between intermittent dynamics. And what you see is that this is a part of a trajectory. And what we are going to do is that we select a set of points in the trajectory and we calculate the convex hull, which is basically the minimal convex shape that encloses those points. So for instance, if you take these blue points over here and you calculate the convex hull, you will see that the shape is very, like the volume of this convex hull is very small. Instead, if you take another set of points, a point in which the particle has been sort of moving much farther away, you will see that the convex hull is much more, of course, bigger, and in a way, the volume is much larger. So without going into the technicalities, but actually it's pretty straightforward. What we do is that we calculate, we take this basically set of points along the trajectories and we just calculate the volume of the convex hull, and then we define an estimator of this. And in this way, it's possible to basically plot, instead of looking at just at the trajectories, we look at what is this sort of time series that we obtain from the convex hull analysis. And we can take some Taylor quantities, such as, for instance, the average of this quantity, what is the value of the peaks, and what is this delta T. We call it slow phase because basically if this particle, they don't move, the volume of the convex hull is very, very small and it stays basically below here. So in a way, by analyzing these three quantities, we can really characterize the dynamics. And I think the most important thing is actually, since I have not much time, the most important thing is this quantity, is this plot over here, that you can see that if we take the distribution of this slow phase, basically the duration of the slow phase, so for how long are the particles just stuck in a cage, you will see that at high density, which is the purple and the red, the two curves merge, and low density you have another sort of curve. So basically, through this convex hull analysis, we are really able to sort of split the two dynamics at low density and high density just by analyzing for how long these particles are in this sort of very local environment, and this is very interesting. And then on the other hand, we can also plot how many of these, like how sort of what is the height of each peak. Each peak would represent, you can think of it as a jump into a next cage. So you will see that basically the height of the peak also depends a lot on the dynamics. At low dynamics, you have sort of it's almost uniform, like sort of a universal distribution, while the higher the density, the more the distribution falls down. So in a way, this has been a method, an analysis that has allowed us really to characterize the two different dynamics and really like look at the fact that at low density we have this intermittent dynamic, which is emerges due to this cage mechanism, and it's due to this typical dynamical heterogeneity in which we have two populations like mobile and immobile particles. On the other hand, at high density, you really have this much more continuous and homogeneous motion. So in this way, basically, what I wanted to show and what I think it's been super interesting is that these studies sort of suggest that you have the energy landscape that is created due to the potential that you have between the particles due to this soft potential leads to a transition between the two regimes, which is a low density regime in which the dynamics is much more similar to just a standard glass former dynamics. At high density regime, instead you have this dynamics which is just much more homogenized, and a way it emerges due to cooperative motion in the system. And these findings are actually very much in line with other works which have been published, for instance, in 2016, in which they've really shown that the Gaussian Core Model, which is the one in red, is very different from standard Lennard-Jones system. But what they studied is only the very, very high density regime. In our work, basically, we were able to connect what is expected at low density and to observe that at low density, we indeed have a standard glass sort of former dynamics, and then to show that there is a smooth transition toward what has been seen at high density, which is sort of a more cooperative motion and very much more Gaussian. Now, basically, what the main question that is there still is that is this dynamical transition that we observe only in the supercooled regime, is it actually an equal sort of due to the fact that there is an underlying glass-glass transition between two different kind of arrested phases? This is still not proved. What we did is just sort of a study in the supercooled regime, and I think this is what we would like to do, is to really understand whether there are actually two different glass in this system. But this work seems to suggest that this is the case. So thank you very much for your attention. And this is a preprint of our work. If you're interested, you can, of course, check it out. Thanks.
Thank you very much. Thank you, Vittoria. So, are there questions? Okay, I have one question. In the part of your talk about results, you have shown the mean spatial displacement, mean square displacement. Okay. In the main panel here, you are changing both temperature and the density. So I assume that if density is constant and you reduce temperature, the plateau appears more clearly and it is longer.
Yes, indeed.
And what about if you keep the temperature constant and you vary the density?
So what happens, for instance, if we select like this temperature, which is 0.004? If you go to very, very low density, the system is fluid. Then, so meaning there is no plateau. Then you start increasing the density, you will see an emergence of the plateau. Then you increase it even more, like you go to density equal 1. At this temperature, you would not observe any plateau. And this is due to the fact that basically the phase diagram is like this. So you would go to fluid, to a sort of glassy, if you want, to another fluid over here.
Okay.
Mm-hmm.
Ah, okay, okay, sort of re-entrant transition.
Exactly. So this system has this re-entrant transition. Exactly.
Okay, okay. Thank you. So, if there are no questions, I think that we can thank again Vittoria. We can thank both speakers. And okay, so we can meet again here in 1 month for the December section, for the, as usual, the second Thursday of the month. So I think that it should be, okay, the 14th of December. And so, okay, good evening to everybody. Thank you.